Hey everybody, this is Mr. Chernitsky, and this is AP Stats modules 4.04 and 4.05. Talking about random variables, in particular discrete random variables, and then binomial random variables. Okay, so when we talk about random variables, we're really talking about like sort of outcomes of things that can happen. Okay, and there's two possibilities that we have. We have discrete random variables, and we have continuous random variables. Easiest kind of way to kind of separate those two is that discrete, we can think of it as distinct and countable. Okay, so an example of discrete would be sort of the outcomes of rolling a die, where you'd have outcomes of 1, 2, 3, 4, 5, and 6. And that's it. Okay, there's no in between, and there's no infinite amount. There's only a specific set of outcomes that are possible. Okay, you could think of other discrete random variables, flipping a coin. Okay, where you have heads or tails. Continuous random variables would be something like the height, or let's say maybe the distance a football is thrown. Okay. The reason this is continuous is that it's not countable. It's not just a, well, it's either 5, 10, or 15 yards. It could be 5.5 or 10.1 or 16.0034, etc., etc. It is a continuous list. Okay, and that's the difference between discrete and random variables. Okay, something that could be related between the two, if you think of it. If we said, did it rain? That is a discrete variable because it's either a yes or a no. But if we said, how much rain fell, that would be continuous because it would be anywhere from 0 to any sort of number, in terms of inches. We could have 0, we could have, 5.231, etc., etc. It's a continuous list. Okay, and that's the difference between discrete and random variables. Okay, no matter what, when we're doing discrete random variables, all of our possibilities, all of our probabilities of our outcomes must add to 1. So in other words, if you looked at flipping a coin, okay, we would assume that the probabilities would be 0.5 and 0.5, and those would add together and add to 1. Or if we're rolling a die, that would be each of the numbers 1, 2, 3, 4, 5, 6. Each of those would be a 1/6 probability, and those would all add up to be equal to 1. Okay, so all of our outcomes, the probability of all of our outcomes must add to 1 in order for this to work. The reason we do this is that this allows us to kind of create functions for our outcomes of having different probabilities, and we can essentially do math of them and do probabilities of things that don't necessarily have a number associated with them. So it doesn't have to just be heads and tails and rolling a die, though we'll look at those situations most often just because they're very familiar and very easily, very discrete, easy to come up with discrete numbers for those. Um, but it very much allows us to kind of create variables. By the way, we use capital letters to define any sort of random variable. Okay, so we might call x as the of an outcome as being the possibility of flipping a heads. All right. When we're doing these outcomes, these probability outcomes, we often create a table. So here is the possibility of hitting, they defined x as the possibility, or say x is the number of red lights, and p of x is the probability that you would hit that number as you're driving to work, let's say. And we can find our average simply by multiplying the probability to that number of possibilities. So if we have a 0.10 chance of running 0 lights, we'd do 0 times 0.10, which would give us 0 and so forth. And we'd add those all together. And we'd get an average of 0.205. By the way, we are using mu as our average, or our mean, not x bar, because when we're doing probability, because we're doing all of these add up to 1, we're essentially looking at all the possibilities. So this is not a sample, this is the entire population. Okay. Same with standard deviation. We are going to use sigma to find standard deviation, or to denote standard deviation. Okay. The long way of doing standard deviation and also calculating is to find variance. So the way we would do that is we would find the deviation from the norm. So our average was 2.05. So for each one of these, we would subtract that value. So we'd have 0 minus 2.05, which gives us negative 2.05. We would then square that and multiply it by the probability. Okay, and then we're going to add all of those for each one of these. We're going to add all of those. And that gives us our variance of 1.4475. And we know that variance is actually the square of standard deviation. So if I wanted standard deviation, I could take the square root. That's the long way of calculating those. We can also use our calculator. So what we want to do is we want to go to our original list. We want to enter that in as 2 separate lists here. So we'll go to stat, go to edit, and we're going to enter in for our first list our x values, so starting with 0 to 4. So 0, 1, 2, 3, 4. Okay, and then for L2 we're going to enter in our probabilities. So that's, oops, that's 0.1, if I remember correctly, 0.1, 0.25, 0.3, 0.2, and 0.15. Okay, and just to note that these should all add up to be equal to 1. So we just did a separate calculator and just show you 0.1 plus 0.25 plus 0.3 plus 0.15. It looks like I'm missing one. 25.3. Yeah, that's right. The probabilities don't seem right to me. Try that again. 0.1 plus 0.25 plus 0.3 plus 0.2 plus 0.15. Okay, I missed one. That's why. Okay, there we go. Double checking. All right. Thought that would be something wrong. Okay. So these have to all add up to 1. Okay, once we get our list, we want to then go to vars. Yeah, we want vars. No, we don't want vars. We want stat, and we want to go to calculate. Yep, and we want one variable stat. So this very first one here. Okay. And our list is going to be L1, and then we want to put in our frequency list is L2. Okay. All right, notice there is a little bit of an issue here. It gives us X bar. This should be mu, not X bar, because this is the whole thing. So don't label on an AP test as this being X bar. That's not correct. This is not a sample because it's a probability. It's the whole population. Okay. They do get the standard deviation correct. Here's our standard deviation of 1.2. So notice that's the exact same thing in both cases. If I wanted variance, just remember variance is our standard deviation squared, so we could take this standard deviation and just square it, and that would give us our variance. We usually don't use variance for anything, but if you needed it, you could do that. So there we go. All right. That's the quicker way, so you don't have to do hand calculations. Transformations, addition and multiplication. So just remember, you can kind of see how we're getting, we get a kind of standard deviation, we get a mean that we're going to end up with some sort of normal distribution, okay, where that's our mean. And we're going to have standard deviations extending out. This is very poor drawing, but you get the idea. We've seen a normal distribution before. Okay, so that would be one standard deviation. Okay, or z-score of 1, z-score of 2, etc. Extending out. When we add to our mean, in other words, if I was, let's say, off by a factor of 1, okay, on our mean here, which was 2.05, okay, let's say I added to that. It was really, the lights got a little more frequent, so we actually had a shift to the right. So remember that adding will shift the mean shifts your mean, but doesn't affect, this is adding, subtracting, does not affect standard deviation, because our hill here, our normal distribution, just shifts to the right, but the standard deviations will still be the same distance apart. Okay. However, multiplication affects both mean and standard deviation. Because by multiplying, if I multiplied by 3, essentially that would expand out my normal distribution and would shift my mean. So both things would get shifted. Okay? All right. So probability and fairness. So in the book they use, I believe, something similar to craps, but I want to look at a roulette wheel. Okay, just kind of illustrate this idea of probability and outcome in real life. So let's say you go to a casino, not till you're 21, right? And roulette is paying 1 to 1 for matching red or black, and 1 to 3. Well, we'll skip that part. Let's look at the red or black. Okay. So we want to know what is our chances of, making some money here. So let's actually create a little chart here. Okay. And our probability of winning will go 0 if we don't win, and 1 if we do win. So let's say we're betting on red every time. Okay. Well, what is the possibility of actually landing on red? Well, there's numbers all the way up to 36, okay, and they're split half between red and black. And then you notice that there's these two greens here. There's 0 and double 0. So what that means is actually is that there are 18 out of the 36 red and blacks are going to be a possibility. But then we also have it could possibly land on the 2 greens. So really what we have is 18 out of 36. Oops. Yeah. As a possibility for a win. Or sorry, not 36. 18 out of 38. Sorry. 18 out of 38, including the 2 greens. And then we have 20 out of 38 would be a loss, right? Either you hitting a black or a green. What that comes out to be is you have about 0.47 approximately and 0.53 chance of failure. Now what that means is, well, let's just take a look at creating kind of a formula. This is we're at a formula. N is our chance to our net gain here. So let's say that $5 is the minimum bet. I haven't been to a casino in a long time, so they may not even do $5 minimum bets anymore. But let's just say we found a table that's doing roulette, $5 the minimum. Okay, what that means if we win, that means they're going to give us $10 back. Okay, that's our win. Okay, and it's going to cost us $5. What that means is, well, if we do a calculation here, our average is actually still going to be 0.47 because 0 times 0.53 is 53, and 1 times 0.47 is 47. We add those together, we still end up with 0.47. So if we look at our average calculation, so on average 10 times 0.47 plus, sorry, I shouldn't do plus, let's clear that. 10 times 0.47, that did not clear it. Clear it. There we go. 10 times 0.47 minus 5. That means on average we are losing 30 cents on average, okay, for each time that we roll. And this is the general, for every game that you would play in a casino, follows this this algorithm. In other words, where the payout is going to be always less than your odds. And roulette's very simple to get that, because all you had to do is add those two green spaces here to offset. In fact, even if you just added one of those green slots, you would offset your balance from being 50-50 to just under 50%. And so, you know, really, even if we looked at our standard deviation, there's still a chance that, you know, we're going to win, but it's not a very good one. I believe our standard deviation, if I calculated it correctly, was 0.04 for standard deviation. If we multiply that times our payout, which is 10, that's 40 cents. So really, we would have to have an n-score, a z-score of 0.75 to even have a chance to start breaking even. So it's not a very good setup to win. All right. This kind of leads us into binomial random variables, because you notice what I did here was, even though there was 3 possible outcomes, red, black, and green, I divided it into 2 possibilities here. Either 0 for, you know, losing, and 1 was a success. Okay, and that's essentially what we do when we talk about a binomial random variable. We want to, instead of having all these possibilities, we want to reduce it to either P is success or Q is failure. Okay, and that's the binomial nature. We either win or we lose. Okay, all of our trials are independent, so that's in this case each roll of the spin of the roulette is an independent. By the way, just if you ever go to a roulette table, you'll see a sign that will show all the previous scores of the roulette, what it landed for, like, well, not all of them, for probably the last like 25 rolls. And that is kind of a sucker board, because you might look at that and say, oh my gosh, it landed on red 5 times, the last 5 times. Well, it must mean that black is going to come up next, right? And that is not true. Remember, all trials are independent. Doesn't matter what happened the previous 25, 50 times. Each new roll is its own chance. Okay. We'll have a fixed number of trials. So in other words, we're going to roll only a certain number of times, and we have fixed probability of success in each trial. That means that our probability is not going to change each time. Okay, that relates back to each independent. So okay, this is the binomial distribution formula, and it looks kind of scary here, but just a couple of definitions. This is actually not too bad. So this is not a fraction, by the way, in this little bracket here. What this is really a this is just an abbreviation for really your conditional conditional probability, which you can also write as NCR. Sometimes you'll see that as NCR. Okay, and NCR is really, if you remember that is n factorial over n minus x factorial. And say conditional. I meant conditional probability, and then x factorial. Okay, so you may have seen that before. Either way, not only is this in your calculator, but this entire formula is in our calculator. So we'll actually do it by hand once, so you can see how it works, and then I'll show you the shortcut on your calculator. Okay. P of x. So that's your probability. X's are that's the number of times that we're going to hit something. So we'll see in the example here. Another possibility, you might see this 1 minus p. This might be actually just written as q, and that makes sense because in the probability of success or failure, well, q is going to equal 1 minus the probability of your success. That just makes sense. So in other words, you add Q and P together, the probability of your success and your failure has to equal 1. Okay. So just in case you see that written differently, just remember Q is actually 1 minus P. Okay. So what is the probability of rolling a 6 5 times in a row? I forgot to write this in here. If we roll sorry, not 6 times in a row, 5 times in a row. 6 was rolling a 6 5 times. Hold on. Scratch that out, I wrote that wrong. If we roll 12 times. Okay. So let's define what we have here. So we're rolling 12 times, so that's our n is 12. Okay. We're trying to hit 5 times, so we're hitting 6 5 times. So that means our probability of success each time is 1/6, and our probability of failure each time, Q, would be 5/6. Okay. All right. Well, let's plug this in. We'll do this as a long way. Okay. So notice that this n over this nx probability, we're just going to put in our factorial. Oops. Okay. So instead of n, we're going to have 12 factorial. And then we're going to have 12 minus 5 factorial times 5 factorial. Okay. All right, well, let's simplify this. Okay. 12 factorial is really 12 times 11 times 10 times 9 times 8 times 7, and it would keep on going, so 7 factorial. 12 minus 5 is going to be 7, so that's 7 factorial. Okay. Well, we can simplify some things here. We've got 7 factorials are going to cancel out. And so in our numerator, we just have 10 times 11, or sorry, oops, 12 times 11 times 10 times 9 times 8. In our denominator, we have 5 times 4 times 3 times 2 times 1. Okay. I could probably simplify a few other things here. If I did 5 times 2 is 10, so scratch those out. Okay. 4 times 3 is 12, so I could scratch out 4 and 3 and the 12. And what I'm left with now is just 11 times 9 times 8, so 11 times 9 times 8 equals 792. So this whole part here is going to be 792, this nx here. So we have 792 times p, which is 1 over 6, raised to the x power, x is 5, times 1 minus p. Remember, that's just q, so I could actually just call that 5/6 there, raised to the n minus x, so that's going to be 12 minus 5, so that's going to be to the 7th power. Okay, so this is our probability of x. Well, let's pull up a calculator. So we have 792 times, parentheses 1, 6, raised to the 5th power times parentheses 5, 6 raised to the 7th power. And that comes out to a probability of 0.0284. I would go at least 4 decimal places. So 0.0284. Oops, calculator. 2.842. Okay, so we're roughly 2.8% chance that would happen. Okay. All right. Let's show you how to do that on a calculator. So we don't need to do all this kind of messy factorial work. You don't need to remember this formula. Okay. If we pull up our calculator and we go to distribution, so it's second vars, okay, and we scroll down and we want binomial PDF. Okay, PDF we want to use for exact values. So we're going to do exactly 5 times. It's not a greater than or less than value. If we're looking at greater and less than, we're going to use the CDF. All right. So we do have number trials. That's going to be 12. The probability success, that's P, that's 1/6. And our X value is 5, okay? By the way, you may not have that question asked. If it just goes straight to this is how you enter that 12, 1/6, 5. And we get the same value, okay? So a lot quicker if we do it that way. Okay. And that is the end of this video.